Okay, we'll begin. Are there questions?
Yeah, sir.
Yes, go ahead, please.
Yeah, when we for the Dirac theory,
Yes,
after quantization, we have four kinds of single particle states,
that's right. Yes,
and we are interpreting them as electrons and positrons with spin up down,
yes,
and the spin value being half.
yes.
At this stage, we could have also said that this is a proton and it's like antiparticle, because
Yes,
right
you
now
could.
we. So why don't we do like? How do we really know that proton is not a fundamental particle like electron?
That's through experiment, right? Because in experimental, you find that if electron has been so this fundamental particle, for example, has certain properties, right? For example, magnetic moment, it has a very specific value of the magnetic moment, and the proton magnetic moment simply doesn't agree with that value. So that's
Okay.
one way of seeing that it's a composite particle. But to first approximation, you can certainly describe protons also as by this Dirac equation.
Like in relativistic quantum mechanics, one can solve proton-related problems to some approximation.
Yes, you can.
Okay.
In fact, originally the theory of protons and neutrons were, given by the Seekowa theory, right? Scalar exchange, right? Which is in a sense an effective field theory, right? That it's not
Okay.
that even though the protons are not fundamental, up to certain energy scale, you can pretend as if they're fundamental, right? If the energies are low enough so that you don't see the structure, then you can approximate the proton as a fundamental particle and you can describe them by Dirac equation.
But the fact that it's a composite particle can be encoded into the theory.
Well, it's a question of what you mean by can be encoded. If you want to describe the proton as a fundamental by this Dirac equation.
No, it's composite in the sense it's made up of multiple particles, right?
Yeah, quarks, exactly.
Yeah. If we add that to the Lagrangian or action, will we get the information that, uh, whatever we see in experiment?
Yeah, so the point is there in quantum chromodynamics, which is a theory of strong interactions, you start by writing a Lagrangian where the
Yeah.
fundamental particles are quarks.
Okay.
And from there, in principle, you should be able to see the proton, right? You should be able to calculate, for example, the mass of the proton. It's a bound state.
Yeah.
In practice, you can get it only to some approximation, right? Because right now the only way people know how to calculate or even attempt to calculate the mass of the proton by putting the theory on a lattice, and then you look for the appropriate poles in the Green's function.
Okay.
And that's how you determine the mass. So that's from the point of view of the fundamental theory. On the other hand, if you want to describe, say, low energy dynamics of protons, right, you can try to use Dirac equation because they are spin-off objects, right? So you can describe protons and neutrons by as Dirac particles with some force, but with some interaction. But you should keep in mind that that's only an approximate description, and it will eventually break down at some energy scale.
Okay.
Any other question?
Sir, that the theory may break down is true for all the kinds of quantum field theories, right? Because we don't know at very high energy what is going to happen.
Yeah, certainly. Certainly. So the point is, for the electrons, at least we know that to the, up to the energy scale that we can actually do experiments, this Lagrangian well describes the theory of electrons, right? The electrons can be treated as fundamental particles. But certainly we cannot know for sure that the electron will remain fundamental all the way up, right? At some point it may break down, and then the electron may turn out to be composites of some other particles.
Okay, yeah.
But with today's knowledge, we think of electrons as fundamental particles, but protons are not fundamental particles. Is that okay?
Yes, sir.
Any other question? Okay, so let me then begin. So let me remind you that so far what we have done is to study source-free Maxwell's theory, okay, which basically is a free theory, okay, just quadratic action, which describes free photons. And we also studied free Dirac theory that describes non-interacting electrons and positrons. So what we are going to do today is to try to put these two theories together. So the first thing that we'll do is to simply add the Lagrangians, okay, without any extra term. So this you can recognize as the Lagrangian for the electromagnetism, and this is the action for the electromagnetism, and this is the action for the Dirac particle. So you just take the sum of these two actions. So this theory has two kinds of fields: the electromagnetic field described by mu and the Dirac field described by psi alpha. And the point to note is that at this stage we have not introduced any coupling between the electrons and photons. Okay, so this is really a free theory, it is a sum of two theories. So if we now go ahead and quantize this, okay, we know that we are going to get 6 types of single particle states. There will be 2 spin states of the electron, okay, which are described by these creation operators and acting on the vacuum. Then there will be 2 spin states of the positron, okay, which are described by the positron creation operators acting on the vacuum. And 2 spin states of the photon, okay, which is described by photon creation operator acting on the vacuum. And of course, this theory will also have general multiparticle states, okay, that will contain arbitrary number of electrons, positrons, and photons. And it's easy to describe those states. They simply correspond to multiple applications of these various creation operators in various combinations acting on the vacuum. And that's the content of the theory. Okay, the particles are free, so if we start with a multiparticle state, it remains the same multiparticle state as time goes. Okay, there is no scattering. So what we are going to do next is to try to introduce interactions between these two systems, right, electrons and photons. But are there any questions at this stage? Okay, so if not, let me then proceed. So before we introduce interactions, let's just say that at this stage, it's a free theory after all. But we can introduce composite operators, okay, that includes both electrons and photons. And if you want to calculate their Green's functions, the time order product, the vacuum expectation of the time order product of composite operators, so you can do that. So here I have given an example. So once you have a theory which has both electrons and photons, okay, as particles, or which has both Dirac field and electromagnetic field as fields, okay, we can, for example, construct a composite operator of this form, right? Psi bar alpha, gamma mu alpha beta psi beta times a mu. Just some arbitrary combination that I have chosen. And similarly, another factor of psi bar gamma nu psi times a nu, okay, but placed at a different point y. And it makes sense now to ask what is the vacuum expectation value of the time order product of these two operators, because both of these are operators in this theory. And because the theory is free, okay, all you have to do is to calculate this by the usual Feynman rules. So you represent this operator by a vertex, okay, which has 3 lines coming out, 3 lines because there are 3 fields involved, one psi bar, one psi, and one a. So the a mu I'll denote by a wavy line. That's the standard notation for the photon. And then the Dirac fields I'll denote by a solid line, but there is an arrow, if you remember. The arrow, the convention is such that psi, okay, the arrow flows towards the psi and it comes out of a psi bar. So for this operator here, for example, there is a psi bar alpha. So the arrow should come out of the psi bar. Okay, so that's why the arrow is away from this line, this vertex here. Psi beta, on the other hand, okay, absorbs an arrow, so the arrow should flow towards psi beta. Okay, that's this vertex, and this is the photon which doesn't need to have an arrow. And similarly, this vertex represents this operator. Psi bar alpha prime, you see alpha prime, arrow comes out of alpha prime. Psi beta prime, okay, arrow goes towards y in this case. And nu of y, okay, wavy line coming out of y. And now to calculate the this Green's function, you have to basically draw all possible Feynman diagrams in which you contract these lines with each other, the fermion lines with each other and the photon lines with each other. But of course, you have to make sure that the arrow is preserved, arrow is correctly matched up. So this is one of the two diagrams that can arise here. The other diagram, which I have not written, is when you have the photon and then the two lines that come out of this vortex join each other, and then similarly two lines that come out of this vortex join each other. So it will be like a wavy line and then two loops on the two sides. So that involves, that's a singular configuration, because that involves SF at two arguments being the same, SFXX and SFYY. This one is non-singular. So here I have written down the expression for this Green's function. So this expression basically involves just putting in the propagators, right? So for this line, for example, you have SF beta prime alpha. Remember that the index of SF are opposite to the arrow. So beta prime comes first, then alpha. Okay, that's the convention we had used. And it's YX, okay, because psi is here, psi bar is here. Okay, so the psi argument always comes first, psi bar argument comes second. So the SF beta prime alpha YX. Similarly for this line, it's SF beta alpha prime. Okay, here is psi, there is psi bar. So SF beta alpha prime, okay, but now it's XY. These are of course part of the of this operator, gamma mu alpha beta and gamma nu alpha prime beta prime. And then finally for the photon propagator, you have to use d mu nu XY. This minus sign can be calculated using the rules that I had given earlier, okay, but today I'll describe also a simpler rule. So you remember the rule that I gave earlier, okay, was that you have to first bring all the psi's to the left of all the psi bars, okay, and then draw lines connecting psi and psi bar and see how many crossings there are. So a shorter way to do this will be not to try to bring psi and psi bar, all the psi's to the left, okay, keep them as they are. So just look at this arrangement over here. Then here you have SF beta prime alpha. So SF beta prime alpha means you have to contract beta prime and alpha, right? So let's look at where is beta prime. This is beta prime. This is alpha. So you contract them like this. And then SF beta alpha prime. So alpha prime is here, beta is here. Okay. So you contract them. And now you can easily visualize that there is no crossing, right? Because beta connects to alpha prime, and then this alpha goes over to beta prime. So lines don't cross. So naively, you might have thought that there should be no sign here. The sign comes from the fact that in one of the combinations, you see here, when the alpha connects to beta prime, it's in the wrong order, right? The psi bar comes before psi, whereas SF represents psi bar two-part function. So in this way of counting, the rule is that you then connect them together. Okay, so you look at how many times lines cross each other. So it's -1 to that number. And then you have to, for every time, you get a pair in which instead of psi bar, you have a psi bar psi. Okay, in that order, you put an extra minus sign. So here, this is psi bar. So that's in the correct order. But this is psi bar psi. So that, because it's in the wrong order, okay, psi bar first, then psi, you get a minus sign. Okay, so that's this minus sign over here. So is this counting clear? Is this point clear? So this is entirely equivalent to what we had described earlier. If you had brought all the psi's to the left and did this evaluation of the sign, you would have gotten exactly the same sign over here. Okay. But this is a shorter process in which you don't have to bring all the psi's to the left of all the psi bars. And finally, this product, okay, you can write actually as a trace and check. Because you see that this combination comes as a matrix product. It's SF beta prime alpha, then gamma mu alpha beta, then SF beta alpha prime, gamma nu alpha prime. Okay. So it's trace of SF, gamma mu, SF, gamma nu. And then I have written d mu nu xy as it is. And this will be a generic feature of Feynman diagrams that after you contract the indices, you can actually write it as a matrix product. Okay. And the general rule, okay, that you find is that the matrix product appears in an order that's opposite the arrow. And that has to do with the fact that whenever there's an arrow, is the beta prime index, that is the index that comes first, and then alpha. So because of this, and similarly for the vortex, right, you have gamma mu alpha beta. So the alpha index comes, the alpha index comes before beta. So because of this, you always get a trace. Okay, you always get a matrix product, and the matrix product appears in the order that is opposite to that of an arrow. Okay, so here, for example, this one is this SFY refers to this one. Then comes gamma mu alpha beta, that's coming from here, then here, and then gamma nu. So that's opposite, that's going opposite in the direction of the arrow. Okay, are there any questions?
Sir, can you please repeat it again? The diagrammatic thing that you said.
Yes, so okay, so this algebraically it's clear, right?
Yes, sir.
Same as this, okay? So the rule that we generally comes out of this Feynman rules is that you get a product of the matrices, right? SF is a matrix, gamma mu is a matrix here. You get a product of the matrices, but the product comes in an order that is opposite to the arrow. So here the product, the first SF comes here, then is the gamma mu that is coming here, the gamma mu is here, then this SF, that's SF xy, and then gamma nu. So the product in which the matrices are arranged in the order that's opposite of the arrow that you have in the diagram. And the trace is not always there, right? The trace is there whenever there is a closed loop. Okay, that closed fermion loop. Okay, that's again another general rule. You can easily convince yourself of these rules. But the universal feature is that the matrices, the way the matrix product arises is opposite to the order in which the arrows are there. Okay, so this one first, then this one, then this one, then this one. Is this clear?
Yes, sir.
Okay. Any other question?
Sir,
Yes.
sir, can we sir, can we see this minus sign from the diagram?
Well, minus sign is best to do in terms of contraction of the in the expression, right? In terms of diagram, it's quite confusing to see the minus sign.
Oh, okay.
Okay.
Because yeah.
Yes, go ahead.
Because in general, suppose I am calculating the cross section for a diagram or something like. So in practice, we first draw the diagram. We don't write this matrix element.
Well, the point is, see, you have to write the matrix element, and the reason is the following, right? So here, of course, both are bosonic operator because there are fermions pair up, okay? Yeah. But in general, suppose you have a set of fermions, right? Inside the time order product. If you change the order of those fermions inside the time order product, then the sign changes, right? Because trace of psi alpha psi bar beta time order product of psi alpha psi bar beta is minus of time order product of psi bar beta psi alpha. Okay. But in the diagram, you don't know which order you have. The operators have appeared inside the time order product. Because in the diagram, you don't see the ordering, right?
Yes, sir.
And that's the reason why it's hard to figure out the sign just by looking at the diagram. You really have to know in which order the operators are inside the time order product.
So we should write this matrix element along with the diagram to find out the sign.
That's that, yes.
Okay.
Any other question? Okay, so then let me proceed. Okay, so far what we have done is we have just taken the sum of the free theories, right? This is what I had said. You have just taken the sum of the free Maxwell's theory and the free Dirac theory. Okay. Now we are going to add coupling between the free Maxwell's theory and free Dirac theory. Okay. Now this coupling is not going to be arbitrary. Okay, we have to follow what we know about electromagnetism. Okay. And what we know from electromagnetism is that in the presence of the source term, when there are charged particles present, the Maxwell's equation has a term on the right hand side. So it takes the form del mu f mu nu equal to minus J nu, okay, where J0 is the electric charge density and Gi is the electric current. And this is conserved. Okay, the divergence, the 4 divergence of J is 0. And because we are trying to describe the theory where the electromagnetism couples to the Dirac theory, describing the theory of electrons and positrons, okay, for the J mu, okay, we'll take the current produced by the electrons and positrons. Okay, so this is the expression for J mu that we'll be using. Okay, minus C psi bar gamma mu psi. Now, this we had discussed once earlier, but you can again convince yourself by doing this calculation that you can achieve this. You can achieve this modification of the Maxwell's equation simply by adding to the action a new term. You add to the action an integral A mu J mu. So the total action now takes this form. This is the free electromagnetism action for electromagnetism. This is the action for the free Dirac fields. And this is a coupling between the gauge field and the Dirac field. Okay, the electromagnetic field and the Dirac fields through this J mu. So J mu, it will be understood. You will be working with J mu, but it will be understood that J mu is always given by minus E times psi bar gamma mu psi. Is this clear so far? Okay. So let me proceed. So the first thing to note is that even in the presence of this term, A mu times this, the symmetry that was responsible for the conservation of J mu is still intact. Okay. So in particular, we have the symmetry under psi goes to e to the I theta times psi bar goes to e to the minus I theta times psi bar. Okay. And the reason for that is simply that J mu is invariant, right? The two phases cancel from here. Okay. So this shows that J mu still satisfies that the divergence of J mu is 0. And that is good because otherwise it will be inconsistent. Because you see from this equation, if you take a del nu on this side, right, then the left hand side is identically 0 because this is antisymmetric in mu nu. And this will be two derivatives that is symmetric under nu mu exchange. So left hand side will be 0. So if the right hand side didn't vanish, okay, there will be inconsistency. So it's indeed necessary that J mu remains conserved, and it does. Okay, otherwise you will not get a consistent theory. But now let's ask about the gauge invariance, right? That's more important, in fact, because we had seen that gauge invariance, in fact, changes the structure of the theory completely. It makes some of the field variables redundant, right? For example, earlier you had found that the time evolution of A0 is completely arbitrary, and that helped us in eliminating some of the variables by gauge fixing. So the question that you need to ask is it still there? Okay, gauge invariance that A mu goes to A mu plus del mu lambda. Now, naively, this is not a symmetry anymore, right? Because you can see that if you look at this A mu J mu, this part of course was invariant. If you look at the A mu J mu term, then A mu J mu goes to A mu J mu plus del mu lambda times J mu, right? Because A mu gets shifted by this. And this is certainly not zero. And in fact, you cannot simply argue that you can integrate the parts and make it this zero, because del mu j mu equal to 0 is not true in general. It's true only when equations of motion hold. Whereas when you talk about whether something becomes symmetry, something is a symmetry, that should hold for all field configurations, right? Not just for those which satisfy equations of motion. So unless you do something else, this is not a symmetry. Okay, just mu goes to mu plus del mu lambda is not a symmetry anymore. Okay, are there questions, comments? Okay. So let me proceed. So here again is the form of the action that we had written down. What we'll do now is to write the action in a slightly different form, okay, by combining this term with the Dirac, with this Dirac action. So here is the new form of the action. So I have absorbed this inside this. So let's check that this gives the correct extra term. So all that has changed here is that besides this derivative, you also have an I e times mu. But you see this I with this I gives to minus. Okay, so that gives to minus e times psi bar gamma mu psi times mu. Right? That's exactly what we had here. Right? Mu j mu is just minus e times psi bar gamma mu psi times mu. Okay. So we have not added or subtracted anything. It's the same action that we had here. Now the claim is that this action that we see here is invariant under a new symmetry in which mu changes by del mu lambda as before. But now the field psi of x changes by a phase, but the phase now depends on x, on the space-time coordinates. And in particular, we take the phase to be lambda of x, the same function lambda of x that appears in the gauge transformation law. So what we are doing here is that we are saying that besides assigning the gauge transformation law to mu, we also assign gauge transformation law to psi and psi bar in terms of x-dependent phase. And the claim is that this is a symmetry of this action. So while just this transformation was not a symmetry of this action, by combined transformation, under which mu changes by del mu lambda and psi changes by this x-dependent phase, that is a symmetry of this action. So is the statement clear? Okay, so we are going to try to check this now. Okay, that this is a symmetry of the action. Okay. So for this, we defined a covariant derivative d mu psi, okay, which is that ordinary derivative of psi and then I mu times psi, that particular combination that appears here. And now let's look at how this transforms under a gauge transformation. So d mu psi, okay, the derivative del mu goes to del mu plus I mu. Sorry, the derivative remains derivative, of course. Okay. And I mu goes to I mu times I del mu lambda. Right? Because mu has changed. And psi changes to e to the minus I lambda times psi. Okay, so that's the way d mu psi changes. Okay, because d mu psi had this, right? You are transforming mu as well as psi. And now you can easily convince yourself that when you take this derivative, right, of course, the derivative can act on psi. If it acts on psi, this phase just comes out. This becomes a common phase. So it can act on psi, but it can also act on this exponential, right, e to the minus I lambda. When it acts on the exponential, okay, it gives a factor of minus I del mu lambda times e to the minus I lambda. And that minus I del mu lambda precisely cancels this I del mu lambda over here. So at the end, what you get back is e to the minus I lambda, this phase, times d mu psi, okay, which is here. So basically, the transformation law of x cancels the transformation that comes from the from this derivative acting on the phase factor. So d mu picks up a phase e to the minus I lambda, psi bar picks up the opposite phase. So psi bar d mu psi indeed remains invariant. So then we reach the conclusion that this action, the coupled action of Maxwell plus Dirac fields, is indeed gauge invariant, provided the gauge transformation laws are changed. Mu transforms exactly in the same way as before, but we allow psi and psi bar to transform by this x-dependent phase. Is this clear? Are there questions? And in fact, this is not, I mean, a luxury, it's necessary. Because if we want to consistently quantize the gauge theory, we do require that the action must have exact gauge invariance, right? You cannot simply say that we add a term in the action which breaks gauge invariance a little bit, okay? Which you can do in principle for global symmetries, okay? Because that basically means that the current that was conserved is no longer conserved, okay? It's maybe gets a small amount of non-conservation. Okay? But for gauge theories, you don't have that choice, right? You have to have exact gauge invariance, okay? Because gauge invariance was necessary to remove certain fields. Okay? So if gauge invariance is broken, then you have to do the quantization of the theory all the way from scratch. Okay? And you may or may not get a consistent theory. Okay? In particular, you can see that if we, for example, add a term to this action, okay, which breaks this symmetry, okay, which breaks the phase symmetry. Okay? If it breaks the phase symmetry, then it will also break this symmetry, typically, right? Imagine you add a term in the action which contains two sides, right? Psi times psi. That will certainly break this phase symmetry, and this will also break the gauge invariance. Okay? Then what is going to happen is that the JMU will no longer be conserved, right? From this structure, and if JMU is not conserved, okay, you see that we run into an inconsistency, because on this here, okay, if you take the derivative divergence, the left hand side vanishes. Okay. If the right hand side doesn't vanish, okay, then you run into an inconsistency. So that's just one manifestation of the fact that in a gauge theory, gauge invariance must be maintained exactly. Okay, you cannot simply add terms to break gauge invariance. Okay, even if the term is very small. Okay, are there questions? Okay, so once we have this unbroken gauge symmetry, the equations of motion still do not fix the time evolution of the fields uniquely. Okay. The argument is the same, right? Because given any solution, okay, you can modify it by gauge transformation, okay, which does not change the initial condition. You can make sure that lambda is say 0 at initially, lambda and its derivatives vanish at t equal to 0, so that initial configuration of gauge fields and fermion fields remain intact. Okay. Nevertheless, at a later time, okay, you can change the configuration, because lambda is a completely arbitrary function. So the equations of motion do not fix the time evolution of fields completely, and we need to fix a gauge, okay, exactly as before. Okay. And what we will now describe is how to analyze this theory using the Gaussian formalism. Okay, so the discussion now will follow similar to what we had earlier, with some few modifications, okay, because of this additional coupling between the Dirac fields and the Maxwell fields. Okay, so if there are no questions, I'll proceed.
Sir,
Yes, go ahead, please.
sir, you said that the equations of motion do not fix the time evolution of fields uniquely, and we need to fix the gauge also. So that some sort of bring us an independence to mold the theory or something.
Well, it's not an independence to mold the theory. The final results should all be invariant and all be independent of how you fix a gauge.
Okay, choosing our gauge should not interfere with the final result or observables.
Exactly, because the observables are all gauge invariant objects.
Yes.
So even if you choose a gauge, f mu nu, for example, is not going to change, right? There is no ambiguity in time evolution of f mu nu. The ambiguity is in the time evolution of a mu, right? Because you can add this derivative of lambda to a mu, but that doesn't change f mu nu.
Okay, so can I say that with the help of this gauge fixing, we can choose the easiest path, or we can construct the easiest path to get to the observables that are gauge invariant.
Yes, that we can say. Yes. So there are formalisms where you don't have to gauge fix. I think I had mentioned it once that in lattice gauge theory, for example, right, you can do the calculation without gauge fixing because you work with only gauge invariant observables. Here in the intermediate stage, you will be working with gauge non-invariant observables. And so, for example, to develop perturbation theory, we do need to gauge fix, right? And that's what we'll do.
Okay.
Okay. Any other question? Okay. So if not, let me proceed. Okay. So I have first written down the Lagrangian. Okay. So this part you will recognize. This is the same as what we had for the Maxwell's theory. This is Lagrangian for the free Dirac theory. And this is the extra term. Okay. So it's the same as the action, except that the integral is now over a 3-dimensional space at a fixed time rather than a 4-dimensional space time. Okay. And again, J mu expression I have written here. So as in the previous case, we are going to use the Rauthian formalism, which means in this formalism, you can treat some of the variables in the Lagrangian formulation and some other in the Hamiltonian formulation. We'll in fact treat AIs as well as psi alphas in the Hamiltonian formalism, and only A0 will treat in the Lagrangian formalism. Okay. In the case of free Maxwell's theory, if you remember, we treated the AIs in the Hamiltonian formalism and A0 in the Lagrangian formulation. So introduce pi I, that's the conjugate momenta to AI, okay, by this equation over here, that's given here. Okay, the definition of pi I doesn't change. See, this is the only extra term that is present, right? The coupling between the Maxwell field and the Dirac field, that doesn't affect the definition of pi I, so it remains the same. Okay. The conjugate momentum to the Dirac fields, okay, is defined here. That's I times psi alpha dagger. That's also the same as what we had earlier. And so the Rauthian is given by the standard formula pi I AI dot plus pi alpha psi alpha dot minus L. So you will recognize that up to this point, it's the same as what we had for in the Maxwell's theory. For the Dirac part, okay, is the Dirac Hamiltonian, the free Dirac Hamiltonian that we had gotten earlier, because as far as the Dirac part is concerned, there is really no distinction between the Rauthian and the Hamiltonian formalism. And then there is this minus A mu J mu, okay, which comes because of this minus L, right? L had an extra term of plus A mu J mu. So in the Rauthian, you get a factor of minus A mu J mu. Okay. So essentially, the Rauthian that we have is the Rauthian of the free Maxwell's theory, the Hamiltonian of the Dirac theory, and then this minus A mu J mu. Okay, so here I have written down the Hamiltonian for the Dirac theory, and the B, I had introduced this concept earlier. This is the magnetic field. Epsilon ijk del j ak, okay, are in the more familiar component notation. B is curl of A. Okay, is this clear so far? Okay. So now we can look at the equations of motion. Okay. And I'll not worry about the equation of motion for the size. Okay, that they can be easily found. Okay, they are the standard Hamilton's equation. Okay. But let's look at the equation of motion for A0. Okay. That's in the Lagrangian form, right? Because A0 we are treating in the Lagrangian form. So this is the Euler-Lagrange equation, ddt of del R A0 dot minus del R del is equal to 0. And you can see from this Rauthian that A0, there is no A0 dot anywhere in the Rauthian. That was a problem for defining pi 0, if you remember. So A0 comes here, right? Delta is A0, there is a del I pi I term. and then there's J0. So the A0 equation of motion simply gives you del I pi I plus J0 equal to 0. And the equations of motion for AI and pi I, okay, we had derived earlier. So AI equation, I think, doesn't change again, right? Del I del T is del R del pi I. This new term that is there in the Rauthian doesn't depend on pi I. Okay, so that's the same as what we had for the Maxwell's theory. And del pi I del T is minus del R del AI. Okay, here we get an extra term GI because R has this minus AI GI term. Okay, so that gives this extra GI term. So far the discussion has proceeded more or less in the same way as the Maxwell's theory, and it will continue to be this way. We'll only focus on the differences, right? The extra terms that come because of these JIs and the J0. Now, as before, we can see that of these equations, right, there is no equation that gives the time evolution of A0. These two equations give the time evolution of AI and pi I, okay, and this is a constant equation, which once you have, once you have demanded this constant equation initially, it will continue to hold for at all later times. Yeah, this you can again check by if you take the time derivative of this, okay, del I del T pi I plus del T J naught equal to 0. That is automatically satisfied, because that you can see by taking this equation and taking the divergence. Okay. When you take the divergence of this goes away. Okay. You get a divergence of J, but divergence of J is nothing but minus del 0 J0. Okay. So that tells us that the time derivative of this is automatically satisfied. So once you impose this initially, that's it. So this part is nice in the form of Hamilton's equation, but A0 has no time evolution. And that, of course, we have learned earlier that it's a consequence of gauge invariance, because you can change A mu to anything that you like by adding this del mu lambda. Not A mu to anything that you like, but for example, A0 you can add to anything that you like by adding del 0 lambda. Okay, lambda is completely arbitrary function. And that's why the A0 time evolution is not determined. Okay, other questions? Okay. So as before, we'll proceed with the gauge fixing, right? We'll choose Coulomb gauge. And the strategy that we'll be following, okay, which is slightly different from the way we did it earlier, okay, but it's the same, it's equivalent. I mean, it's a question of at what stage you do this change from the position variable to momentum variables. Okay. So at this stage, we are going to express the Rauthian using momentum space variables. Okay. So I'll introduce all these momentum space variables: a tilde I, pi tilde I, a tilde naught, psi tilde alpha, pi tilde alpha, etc. Okay. I have only written down the expression for AI, the relation between AI and a tilde I, but the same relation holds for every one of these variables, right? Just the Fourier transform in the spatial variable, spatial components. Okay. Time, of course, remains as it is. And once we have gotten this, okay, we'll write the Rauthian in terms of these new variables, tilde variables, the Fourier transform ones, and then we'll try to eliminate some of the variables using their equations of motion. Okay, and we'll see how exactly this is done. Okay, other questions? Okay. So as before, we are now going to introduce these basis vectors, epsilon A, which are transverse to P. Okay. So epsilon A's are two basis vectors, three-dimensional basis vectors that are orthogonal to P, okay, and they are orthogonal to each other, orthonormal to each other. So epsilon A dot epsilon B is delta AB. Okay. And this is a convenient choice, although it's not necessary. Epsilon A of minus P will take to be epsilon A of P. So given this, we'll define a tilde I to be the component of a tilde along the epsilons. Okay, so a tilde I is epsilon aj times a tilde j. Similarly, pi tilde I, the component of pi tilde along epsilon. And a tilde parallel and pi tilde parallel, these are the components of a tilde and pi tilde along the momentum vector, along the unit vector, along the momentum with an extra factor of I, okay, which is for convenience. So A tilde parallel is given by I pj A tilde j over mod p, and pi tilde parallel is I pj pi tilde j over mod p. And you can also reverse these relations, right? Because A tilde and A tilde parallel are components of A tilde along the these three orthogonal vectors. We can now write A tilde itself as a linear combination of these orthonormal vectors, right? With the coefficients being these projections. Okay, so A tilde j is given by this, and pi tilde j is given by this. Okay, are there questions? So you are doing this because ultimately you want to write the Rauthian in terms of these variables that you are introducing here. Now, to simplify the expressions, we will also introduce the Fourier transform of J. J, remember, is a composite object, right? J is psi bar gamma mu psi times minus C. But nevertheless, nothing prevents us from introducing its Fourier transform. So J tilde mu Tp is defined by this Fourier relation. Okay, you can also write the inverse relation, J tilde mu in terms of J mu. And we will define J tilde A and J tilde parallel exactly as before, right? J tilde is the component along the epsilon vectors, and J tilde parallel is the component along the unit vector along P. Okay. And just like we could reverse the relation and write A tilde J in terms of these components, I can also write J tilde J in terms of these components. So in the next slide, I'm going to express the Rauthian in terms of all these new Fourier transform variables that we have introduced. Okay. Is this okay? Are there questions? Okay, so let's then proceed. Okay, so this was the expression for the Rauthian, if you remember, okay, in the position space. And now the claim is that if we now re-express this in the momentum space, this is what we get. Now of this, some of the terms we had already gotten earlier when we were discussing free Maxwell's theory. Okay, so those terms I'll not discuss anymore today. Okay. So these three terms, for example, the first line, the three terms here basically came from these two terms over here, the free part of the Maxwell theory. These two terms, and okay, maybe, yeah, it came from these two terms over here. Then here you see this A naught del I pi I has become A tilde naught times mod P times pi tilde parallel. Okay, you can easily see because you see pi I, let's look at it. Okay, so basically what happens is that when you take the del I of anything, so suppose you have a pi I here and pi tilde I here, when you take the derivative, you bring down a factor of IPI, right? Because del I brings down a factor of IPI, and this is precisely the definition of A tilde parallel. Okay? That's how we get the del I pi I here becomes mod P times pi tilde parallel. Okay, because the IPJ term has automatically gotten absorbed inside the pi. Then you have a minus A0 J0 J tilde 0 that's coming from here. Then you have minus A tilde parallel J tilde parallel also coming from here, and minus A tilde A J tilde A, okay, also coming from here. Okay, so these are the three extra terms that you have, which was not there in the free Maxwell's theory, right? The coupling to J. Okay, up to this point, what you have is also present in the free Maxwell's theory. And the Dirac Hamiltonian, I'll not try to re-express in terms of momentum variables, but it can certainly be done. I'll just write it as HT. Okay, but it's understood that you can also write it in the momentum space variables. Okay, are there questions? Okay, so given that this is a Rauthian, okay, we'll now try to write down the equations for A tilde 0, A tilde parallel, and pi tilde parallel. And for this, you have to keep in mind that the A tilde 0 is being treated in the Lagrangian formulation. And these are being treated in the Hamiltonian formulation. Because A tilde parallel and pi tilde parallel are basically coming from A tilde I and pi tilde I, right? And A tilde I, AI and pi I, we have already decided that we will treat in the Lagrangian, in the Hamiltonian formulation. That's how the Rauthian was constructed in the first place. So the A tilde naught equation of motion takes the form of the Euler-Lagrange equation here. So let's see what we get here. There is nothing which depends on the time derivative of A tilde naught. So this term is 0. So you just get del R del A tilde naught equal to 0. And that gives you this equation. Mod p times pi parallel plus J tilde naught equal to 0. And this you may recognize just as a Fourier transform of something that you already saw in the position space, this one. Sorry, this one. Okay, that what the equation that you saw there in momentum space is just the Fourier transform of this equation over here. Okay, so that's here. Then A tilde parallel equation of motion. Okay, this is in the Hamiltonian form. So time derivative of A tilde parallel is the derivative of the Rauthian with respect to pi tilde parallel. Now, one point you notice here is that to get the equation for del t A tilde parallel, I am taking the derivative with respect to pi tilde parallel, but tu minus p. And this comes from the fact that A tilde I t minus p and pi tilde I tp are in fact conjugates of each other, right? There is a change in sign in p. To see this, you just notice that if you take the Poisson bracket, this was our Poisson bracket in the position space. When you translate this to the momentum space, you get AITP with pi tilde j t p prime as delta q p plus p prime, which basically sets p prime equal to minus p to get a non-zero Poisson bracket. Okay. That's why pi tilde j t minus p is conjugate to A tilde j tp. Okay, that's why we are taking the derivative with respect to pi tilde parallel t minus p. So this derivative, let's see what we get. So pi tilde parallel is here. So you get one term that is minus mod p times A tilde 0. Okay, that's here. And then there is a pi tilde parallel square. This is half. So that gives a pi tilde parallel. And I think that's all the pi tilde parallel you have here. So you get a pi tilde parallel minus mod p times A tilde 0 equal to 0. Sorry, equal to del t A tilde parallel. And finally, del t of pi tilde parallel is the derivative of the Rauthian with respect to A tilde parallel t minus p with a minus sign. And A tilde parallel is here, right? In fact, that's the only place where A tilde parallel appears. So that gives you J tilde parallel tp. So these are the equations of motion for A tilde naught, A tilde parallel, and pi tilde parallel. And the idea is that we'll use these equations of motion to eliminate these three variables altogether from the Rauthian. Are there questions? Okay, so let me again remind you that these are the three equations. Okay, and now we are going to also use a Coulomb gauge condition. Okay. So the Coulomb gauge condition was divergence of A equal to 0. Okay, but in terms of A tilde parallel, it takes the simple form of A tilde parallel equal to 0. Because when the derivative again becomes P dot A. Okay, and that's nothing but A tilde parallel. Now, using this, we see that we can now eliminate pi tilde parallel. Sorry, this should have been a pi tilde parallel. Okay, not pi parallel. We can eliminate pi tilde parallel. Okay, that's minus J0 over P, J0 tilde over P. Okay. Then in the second equation, okay, we can eliminate A tilde 0 because A tilde 0 is, okay, this is 0, right? Because A tilde parallel is 0, so this vanishes. So A tilde 0 is pi tilde parallel over mod P. That's using this minus 1 over P square times J tilde 0. And now we can see the third equation holds automatically, this equation. You see, you have no choice, right? Pi tilde parallel has already been determined here. That's minus 1 over mod p times j0. So if you now check the third equation, right, del t of pi tilde parallel, you get minus 1 over mod p, del t of j tilde 0. But del t of j tilde 0 is by conservation law, right, del I ji or del I j tilde I, and that gives you mod p times j parallel. So this equation automatically holds. Okay, you don't have to impose it separately. Okay. And this basically means that if we set a tilde parallel equal to 0, pi tilde parallel equal to minus 1 over mod p j tilde 0, and a tilde 0 is equal to minus 1 over p squared times j tilde 0, okay, we can simply substitute this in the Rauthian, okay, and regard that as a Rauthian for the rest of the variables. And it's important here that these equations are all algebraic, right? I mean, if the equation had some time derivative of these variables, then of course you couldn't eliminate it. Then it doesn't make sense to eliminate it, because then you have to do an integral, right, to have a time derivative. But for these three variables, okay, a tilde parallel, pi tilde parallel, and a tilde 0, all the equations are algebraic, and that's the reason why you can eliminate them. So what we are going to do is to simply substitute these in the Rauthian and see what we get. Okay. Are there questions? Okay, so let me proceed. So here is the Rauthian again. Okay, the starting Rauthian. Yeah, I have not done anything so far. This expression is exactly identical to what we had here. Okay, the second expression over here. Here are the solutions to the equations that we had found. Okay. So now, as I said, the idea is that we will simply substitute this in the Rauthian, okay, and express the Rauthian in terms of these transverse variables, pi tilde and a tilde. Okay, those are the only two variables that will be left over, except of course the Dirac fields. Okay. So let's see. Suppose we substitute this in the Rauthian. Okay. You get this as before. This term pi tilde parallel square, okay, gives you 1 over mod p, 1 over p squared times j tilde 0 t minus p j tilde 0 tp. Okay, that's this term over here. This one remains unchanged. Okay, we are not going to touch this a tilde a. This one is 0, okay, because you see pi tilde parallel is given by minus j tilde 0 over mod p, right? So this term vanishes. You can set this equal to 0. A tilde parallel is 0, so this also vanishes. So you are basically left with this. So minus integral d cube p a tilde t minus p j tilde tp, and then of course the Dirac Hamiltonian. Is this clear? Are there questions? So now the idea is that we'll simply regard a tilde a and pi tilde a as the conjugate variables, and simply proceed with this by to quantize this. Now we can just regard this as the Hamiltonian, right? Because now there is no variable left in which is to be treated in Lagrangian formulation, right? A tilde 0 has already gone. So now this Rauthian is as good as a Hamiltonian. Okay, we'll treat this as the Hamiltonian for the set of variables a tilde a, pi tilde a, and the psi dagger, okay, and proceed to quantize it. Okay. So here is an exercise, okay, that is to check that when you derive the Hamiltonian form of the equations of motion from this Rauthian, okay, these equations that you will get from here, okay, together with the equations that we had initially, namely these three equations, okay, they are entirely equivalent to the equations of motion derived from the original Rauthian. Okay, this of course follows from this construction, okay, but it's good to check it independently. Okay, so the equations of motion for all of these variables, okay, the Dirac fields as well as the gauge fields that you derive from this Rauthian, okay, is the same as that you had derived from the original Rauthian, which is here. Are there questions? Okay. So now the idea is that we will try to quantize it. Okay, and to quantize it, we'll use perturbation theory. Okay, so you have to divide this into a free part and an interacting part. Okay? And you will take to be the free part the ones that we had in the free Maxwell's theory plus a free Dirac theory. Okay? So those are the terms that are, this term was there in the free Maxwell's theory. This was there in the free Maxwell's theory. So these are the two terms that we'll have keep as part of the free Hamiltonian. Okay? This is a part of the free Hamiltonian because it is just quadratic in the Dirac fields. Okay. So I'll write R as H free plus H interaction. H free is given here. Okay. And the rest is H interaction. Okay. So the rest includes, I think I have put a minor, may have made a minus and errors. No, this is okay. Okay. So rest includes this term, right? 1 over 2p squared J0, J tilde 0, J tilde 0 term. Okay. That is here. Okay. And then there is this minus A tilde J tilde term, right? That is coming from here. Okay. So this is interaction, okay. And this is also interaction term. Okay. And the reason is that you see these involve more than 2 powers of fields, right? Usually the terms that contain quadratic terms in the fields are part of the regarded as part of the free Hamiltonian. This is quadratic in the pi's, this is quadratic in the a's, right? HD is quadratic in the psi and pi. Okay. But this one is quartic, right? It has a psi bar side and psi bar side. Okay, it has 2 psi bars and 2 psis. This one, on the other hand, has 1a and 1 psi bar, 1 psi, right? So this is a cubic coupling. Okay, that's the reason why these 2 terms we are regarding as part of the interaction terms. Okay, so that's here. Okay. Are there questions, comments?
So,
Yes, go ahead, please.
sir, I have a confusion which I want to clear.
Yes.
Sir, like we are adding a source term in free Maxwell theory, which is a Dirac field. Source term is a Dirac field. Sir, we are trying to see the interaction between the photons and the fermionic particle. Basically, we are doing and finally then we calculate the probability outcomes.
Yes.
Uh, Yeah, okay. Sir, it's my confusion that I want to clear.
Yeah. So that's the goal, that we want to couple the
Okay.
photons and for electrons, right?
Okay.
And we do it by simply using Maxwell's theory, right? Because you know that in the Maxwell's equation itself, there's a coupling between electromagnetic field and the electrons, right? Because electrons are charged. So that's the extra term we added to the Lagrangian.
Okay, sir. Okay, sir. Also, sir, one more thing. Sir, sir, what's physically meaning of like gauge fixing? We add field, we add a term in a field like we are trying to see the invariant of action or other things. Like, I just want to know.
Yeah. So gauge fixing basically means that, I mean, as we saw that we have this freedom, right? Because given mu, let me go back. Okay. That given any solution, right, we can always add a del mu lambda, and that's a equally good solution. Okay. Now we also know that these 2 solutions have the same f mu, right? So there's no ambiguity in the gauge invariant quantities. Okay. It's just because if you use the gauge field, the mu's as the fundamental variables, then you have this problem that the time evolution is not uniquely fixed. So gauge fixing basically means that you just put an ad hoc rule as to how you evolve in time. The ad hoc rule that you are putting is this Coulomb gauge, right? Where you simply demand divergence of A equal to 0. Okay, and we had seen earlier that you can always choose this gauge, right? Given any configuration, you can always make a transformation like this to bring it to the form where divergence of A becomes 0. Okay. So the gauge fixing is just a trick by which you make the time evolution of the gauge fields unique. And that doesn't affect any physical quantity because the F minus, right, which are the gauge invariant quantities or other gauge invariant quantities, they all are independent of this gauge fixing.
Okay, sir. Okay.
Okay, so gauge fixing is simply removing this freedom of being able to transform mu by del mu lambda.
Okay, sir. Okay.
Yeah, but it's important to keep in mind that the final results are all independent of the gauge fixing choice that you make.
Okay, sir.
Any other question? Okay. Okay, so here is the formula again. Okay, so Rauthian is the part of the sum of the free Hamiltonian and interacting Hamiltonian. The free Hamiltonian is given here. The interacting Hamiltonian is given here. Okay. And the idea now is that we can now proceed to quantize it and calculate the Green's functions using perturbation theory. And to do that, we follow exactly the same procedure as for interacting scalar field theory. Okay. So the analysis is identical, so I'm not going to write down, do the analysis again. Okay. But I'll only quote the final result. Okay. So the result is that if we try to calculate the expectation value of the time ordered product of, say, a bunch of operators, which can involve the A tilde is, okay, I'm working in the momentum space here. Okay, partly moment, the spatial part I'm writing in the momentum space variables. Okay. We can take an arbitrary product of A tilde is, okay, psi tilde alphas and psi bar tilde betas. This time ordered product is given as a ratio of a numerator and the denominator factor. In the numerator, what you have is the expectation value. This time is in 0. What is 0? If let me remind you that 0 we had defined to be the vacuum of age free at T0. Okay, T0 is an arbitrary choice of time. Okay. Age free is given here. Okay. So 0 is the vacuum of age free of T0. Okay. The index I here means they are interaction picture fields. Okay. Interaction picture, let me remind you, is where the fields evolve, okay, by Heisenberg equations of motion, except that the Hamiltonian, effective Hamiltonian with which you evolve the fields, is not the full Hamiltonian, but by h free at T0, right, which you had called H0. Okay. So the analysis is identical. Okay, you just replace the scalar fields by these other fields, but otherwise there is no difference. Okay. And you will find that the time ordered product of fields, the vacuum expectation value of time ordered product of fields is given by the ratio of this kind, okay, where numerator involves the product of this interaction picture fields times exponential of minus I integral hi of tau d tau, okay, from minus, this integral again is from minus t times 1 minus I epsilon to t times 1 minus I epsilon, the same formalism, and the denominator is given by the same similar expression, except that there are no insertions here. Okay. And because this is the vacuum of h free of T0 or H0, okay, and because the interaction picture, in the interaction picture, the fields evolve by H0, okay, which is a free Hamiltonian. Okay. The matrix elements in the numerator and denominator are just Green's functions in the free field theory. Okay. So you can evaluate these using the Feynman rules as before. Okay, the Feynman propagators are the Feynman propagators of the free fields. Okay. So this you can now compute using Feynman diagrams. Is this clear? Okay. So this formula, you should just look up this analysis in the scalar field theory. It's identical formula, right? It's a ratio of numerator and denominator, where numerator involves sum over all Feynman diagrams, and the denominator basically is the sum of bubbles, okay, which will remove the bubble diagrams from the numerator. Okay. And this is, again, I should emphasize that because H free, the way I have chosen H free, okay, is identical to what we had in the free Maxwell's theory and free Dirac theory, right? HD is the free Dirac Hamiltonian, and this was the free Maxwell Hamiltonian. Okay. We don't have to do any extra work to find out the new propagators and anymore, right? Because the Feynman propagators that we use in the perturbation theory will be the same as the ones that we had used in the free Maxwell theory and the free Dirac theory. Are there questions? Is this clear? Okay, so I'll proceed. So here is a summary of everything else again. Okay, the Raoutian is the sum of free Hamiltonian and interacting Hamiltonian. Free Hamiltonian is given here. The interacting Hamiltonian is given here. Now, if you remember in the Maxwell's theory, right? If we had tried to directly use this Hamiltonian, right, we have to deal with this index A. And dealing with the index A means you have to keep track of those polarization vectors that we introduced, the epsilon A's. So in the free Maxwell's theory, to calculate the Green's functions, we in fact went back to the original mu variables. So here we will try to do something similar, but it will not be exactly what we had for the free Maxwell's theory, and for reasons I'll explain. So our goal here is to avoid dealing with the index A. Okay, this is a technical. This is just for convenience. You can, in principle, you can just proceed with this itself, right? Derive the Feynman propagators for the A tilde S and work with this. Okay, but I'll try to use a more coherent formulation where you don't have to keep track of the epsilons. So we introduce a variable a mu. Okay, this Carly a mu. This is different from the original Maxwell field a mu that we had in the theory. Okay. We introduce this Carly a mu and its Fourier transform, which are denoted by Carly tilde a mu. And these are defined as follows. Okay, so we define Carly a mu. This is the Fourier transform variable T and P by this linear combination of the A's. Okay. Eta bar A, okay, let me remind you, is basically its time component is 0 and its space component is epsilon A. So this Carly a mu tilde doesn't contain any more information than the A's, right? It's basically A's, okay, but we have defined this Carly a tilde mu with all 4 components. Okay. For example, the 0 component is 0, okay, and the parallel component is also 0, right? Because it's along the transverse directions. So if you take the pi a tilde I, for example, it will be 0 identically, because pi a tilde I will be pi eta ai, right? That is p dot epsilon, and that is 0 by construction. So if you compare this with the free Maxwell theory, okay, for the free Maxwell theory, we had a tilde mu given by exactly a similar expression. So this means that the propagate when you use the interaction picture, right, where you evolve by the free Hamiltonian, the Feynman propagator for ai mu will be the same as that of a mu in the free Maxwell theory, and that we had called d mu nu of xy. Now here, let me remind you, let me emphasize that why we had to introduce this Carly A, and why we couldn't go back to our original gauge field a mu. The reason that we didn't go back to the original gauge field a mu is because for the a mu, a0 is not 0, right? Let me remind you, a tilde 0 is not 0 in the presence of a source. See, a tilde 0 is given by this minus 1 over p square term j tilde 0. A tilde parallel is still 0, but the a tilde 0 is not 0 anymore, right? That's why I introduced this Carly a tilde, which by definition has 0 component 0. And that's why Carly a tilde is not the same as original a tilde. If we had worked with original a tilde, then the propagator, okay, of the original a tilde will not be the same as the free Maxwell's theory, because it will have this additional term, right? It will have a j tilde 0, j tilde 0, which in fact is a complicated interaction term. So just to avoid this, we introduce this Carly a tilde. So that Carly a tilde behaves in the same way as the original free Maxwell A, okay, not the interacting Maxwell A. Is this point clear? So the claim is that if we work with this curly A, its propagator will be the same as the propagator of mu in the free Maxwell theory, because propagator after all is coming from the A 2-point function, right? Because that's the source of the propagator. And as long as this equation is the same as this equation, the A tilde 2-point function that you calculate from here is the same as A tilde that you calculate from here. So in terms of this curly A tilde, we can now rewrite the interaction term in the following way. This part is the same. Okay, that part has nothing has changed. This part I'm writing now as minus A tilde mu t minus p j tilde mu tp. Okay, because after all, A tilde mu has only the transverse components non-zero, as you can see from here, right? So once you substitute A tilde mu, okay, you will get back the A j term. Okay, nothing else will survive. A0 is 0 anyway, and A tilde parallel is 0 anyway, so there is no J0 and J parallel term. And this is in the momentum space. You can also rewrite this in the position space now. So this, of course, has a very simple translation to position space. That's here. For this one, you have to do a little more work, because it's 1 over p square sitting over here. Right? So in the position space, if you write j tilde 0 as integral d cube r over 2 pi to the 3/2 times e to the ip dot r times j tilde 0 tr, right? If you substitute, you will find that this is given by this the two integrals d cube r prime, okay, because of this 2, and then there is a grr prime, okay, which is given here. Okay, this is basically the Fourier transform 1 over p square that's coming from here. And this one, in fact, we had seen earlier. Okay, this one, you can see that it satisfies the nabla square g is equal to delta r minus r prime, right? Because if you take the divergence square of g, the gradient square of g, right, that brings down a factor of minus p square. So minus p square, that minus sign cancels this minus sign, p square cancels this, and you get delta cube r minus r prime, right? That's precisely the definition of the Green's function. So grr prime is given here, okay, which can also be written like this. Is this clear? Are there questions? Okay, so this part of the Hamiltonian, right? This part, you can in fact recognize. You see what is it? It's half, and then there is a 1 over 4 pi 1 over mod r minus r prime. That's like the Coulomb potential, right? So these are the charge densities. J0, J0, right? Charge density at r, charge density at r prime. And then this is the Coulomb interaction term. So this one is what is normally called the instantaneous Coulomb interaction, right? This has interaction at equal time, okay, separated by space. Okay? And the interaction strength is 1 over mod r minus r prime, exactly as in electrostatic. This is electrostatic energy between the two between charge sources. Okay? So this part of the Hamiltonian is the instantaneous Coulomb interaction. Okay? This is the additional coupling, okay, between the Maxwell field and J mu. Okay? But this is somewhat of a, you can call it truncated Maxwell field, because A0 is 0. Okay, that's why Coulomb interaction has been separated out. Are there questions?
So doesn't this look like a non-local thing, like the first term?
Yeah, indeed, it does look like a non-local thing, right? And if this term was, if we only had this term and not the second term, okay, then this will violate causality, right? It will have instantaneous interaction, action at a distance. Okay? But you will see that this term, in fact, gets cancelled by something from over here.
Okay.
Okay, so this is indeed looks non-local, right? See, the original theory was perfectly local, right?
Yeah.
So you don't expect that you should have non-local theory at the end, right? And indeed, we don't have. But the way you have written it here, it does look like a non-local interaction.
Sir, isn't
Is
that
it
a problem
because
that,
Yes, go ahead, please.
yeah,
yeah,
I'm saying, is it because we are quantizing it in a non-covariant way?
You can say it that way, right? But there are other covariant ways of quantizing which also may have this feature, right? The point is here, of course, we have done various manipulations. You have split the Hamiltonian in different ways, right? Given a local interaction, you can always write it as a sum of two terms, each of which is non-local, and the sum gives you local interaction, right?
Yeah, but the interaction term itself contains a non-local term and a local term. So there is not,
See, okay,
another
okay,
non-local.
yeah, this one actually is not local, okay, because if you remember the definition of a mu, right? A mu is given in terms of the a tilde mu, which is this split. This is,
Yeah.
and a tilde 0 is set equal to 0 by hand, right? So this is not, in fact, a local field, right? Because you have gone through the momentum space. You cannot write, for example, this curly a mu in terms of the original local field a mu as a local relation.
Okay. Yeah. Okay.
Right? So this is also non-local, right? Even though it looks local, right? Because I have introduced this curly mu. Right? So this has an intrinsic non-locality because curly mu is not a local function of original mu, right? And that non-locality basically is going to cancel this one.
so, but that might be true other way around also, right? Like if you were to start with a non-local apparently non-local Hamiltonian or action, it might be possible that there are some cancellations in like within the theory.
Yes, indeed, that's possible, right? Except that there we don't know how to do that, right?
Don't know in the sense like a convenient formalism. Yeah, we don't know.
Meaning if we randomly write down a non-local Hamiltonian, right?
Yeah,
It's going to remain non-local. It's not going to give a local theory at the end, right?
Yeah.
You have to be extremely lucky that you randomly write down a non-local Hamiltonian and eventually recover a local theory.
My point was that we specifically add covariant terms to the Hamiltonian or action in the sense that we demand that action does not vary under a Lorentz transform, let's say. So we add terms like a mu, j mu, and other.
Yeah, but you also that is something more. You also demand that the action should be local, right? You write the action as a single integral.
Yeah. But at the end, if there can be these sort of cancellations, which are, here we know it since because it was local to begin with.
Yes.
But maybe if you would hand out this form of the Hamiltonian to someone, maybe it's not that clear.
Yeah, exactly. So it's certainly possible, right? This is an example that you write down a Hamiltonian. If somebody gives you this Hamiltonian, right? This is entirely equivalent to the original Hamiltonian.
Yeah.
But it's just that if somebody gives you this Hamiltonian, somebody could, it's very unlikely that somebody would have discovered this Hamiltonian at random, right?
Yeah, that is true. But
so it's just a question of how, what is the systematic way to proceed local quantum, construct local quantum field theories, right? It's certainly possible that you can write down a non-local action which eventually gives a local quantum field theory. But there is no systematic procedure for doing that.
Okay.
Right? That's why we try to start with a local action, right? But there are known quantum field theories which have no action principle, right?
No what?
No action principle. You don't know how to write a Lagrangian for those quantum field theories, even though you don't know that the quantum field theory exists. There are various consistency relations by which you can calculate the Green's functions.
Okay.
And it's possible that maybe there is some way to write down non-local Lagrangian for those. But it's in general very hard, right? Because if you write down a non-local Lagrangian, right, then most likely it's going to give a non-local theory.
Yeah.
Right? You have to be extremely lucky to get a local theory by randomly writing down a non-local Lagrangian.
All right.
Okay, are there other questions? Okay, so maybe I'll start with this next time. Okay, so now basically, so next time what we're going to do, that's tomorrow, okay, is to start with the action, with the Hamiltonian, and then write down the Feynman rules. Okay, then we'll find the propagators interactions, right? So for example, we will get propagators like this, interaction vortices like this, and then we'll proceed from there. So maybe today I'll stop here because it's already past time, and then maybe another class after this. But if there are questions, we can take more. Yes, go ahead, please.
Sir, you said that they in the Hamiltonian, in this Hamiltonian interaction Hamiltonian, the second part is also non-local, although it seems to be.
Yes.
And you said that this is because it is not a function. The curly mu is not a function of local function of mu.
Yes, that's right. Because you look at the definition of curly mu, right?
Yes.
Curly mu is defined by this equation over here, right?
Yes.
Whereas mu had many other parts. In general, right? The capital mu also had a A0, right?
Yes, sir.
You set it to 0 by hand.
This curly mu. The curly mu.
Curly mu is set, the 0 component you set equal to 0 by hand, right? Which is not the same.
Yes.
Which is not the case. Which was not the case for capital mu.
By introducing this at a forward.
Exactly. Yeah. That's why it's not a local. So there is an intrinsic non-locality even in this term. Okay, even though it's not visible.
Okay.
And these two will basically cancel.
So I have another question.
Yes.
Do other gauge theories have this thing that we can choose arbitrary gauge? We won't have a specific time evolution of one component of gauge.
Yes, all gauge theories by definition have this property.
Yeah, they should
because
have.
Gauge theories involve local functions, right? The transformation parameters are local functions, which can depend on x, right? Which basically means that you have the function worth of degrees of freedom, right? Which is arbitrary. And using these, you can show that the time evolution is never unique for gauge theories. So all gauge theories have this property. And you have to do gauge fixing appropriately.
Okay. Can you a bit more some? I don't completely comprehend it.
Okay. So what I'm saying is that the reason for time evolution not being unique, right, is this feature. Let me go back here. Yeah, that given an mu, right, you can add to mu a del mu lambda. Now, the lambda can be chosen in such a way that, say, del mu lambda is 0 at t equal to t naught. And maybe even its first time derivative is 0 at t equal to t naught. But lambda is non-zero and non-trivial function for other times. Which basically means that if you make a gauge transformation like this, it's not going to change the initial condition. Because at t equal to t naught, mu is the same as what it was before. The derivative of mu is the same as what it was before. Nevertheless, at a later time, mu can be changed arbitrarily, right? Mu is not unique. So that's what is showing that the time evolution of mu is not unique. Okay, once you have a gauge symmetry. And whenever you have a gauge symmetry, this is a property. Right? It's a feature, right? Because if you have a function worth of variables that you can add to modify your field configuration, then you can, by adjusting the function appropriately, you can make sure that the initial values are not changed, but at later time the fields are changed, right? And that's what one means by saying that the time evolution of mu is not fixed uniquely.
Yes. Okay. Thank you, sir.
So this is a very specific feature of all gauge theories, right? Not just for Maxwell's theory. The other question?
Okay, sir.
So,
Yeah.
is there an algorithm for quantizing, not quantizing, like to deal with the first class constraints as we did for the second class constraints? I mean, we used Dirac bracket to quantize systems with second class constraints. So, what would we do with first class constraints?
Yeah, the first class, the Dirac's procedure also lays out what to do for first class constants, right? If
Yeah,
you,
I mean, he says that we can, I mean, all those wave functions should be such that the action of first class constraint considered as an operator should give zero.
yes,
In this
that's
but
one way to impose that you impose the constant, the first class constants acting on the wave function gives you zero,
yeah,
right? So first class constants, in fact, are what is responsible for gauge transformation, right? The fact that you have a gauge invariance like this, that you can also think of, see it by saying that the first class, the commutator of the Poisson bracket of the first class constants with the fields generates gauge transformation. So gauge theories, right, when you try to quantize using Dirac's procedure, will always have first class constants. And imposing that the first class constant acting on the wave function gives you zero, right, is a statement that the wave function should be gauge independent.
Okay.
Right? That if you think of the wave function as a functional of the fields, then if you change the argument by a gauge transformation, the wave function should remain unchanged.
Okay.
Right? That's the physical meaning of why the first class constant acting on the wave function should give you zero.
I mean, is that the only way we can deal with first class constraints? I mean,
No, there are various ways of quantizing gauge theories. Right? In the GFT2 course, for example, you will see the BRST quantization, right? For the pop-up, that's the standard procedure that one follows now, right? Not the canonical formulation that I'm doing here. Okay. See, canonical formulation is most useful for understanding physically what you are doing, right? Because you see the states, you see the interactions, you see the scattering. Okay. But the common way that one uses these days the procedure that one uses for calculating scattering amplitudes and Green's functions is by using path integral. Okay. And when you do path integral, there are different ways of dealing with gauge symmetries. Right? And the standard procedure that is used now is the BRST quantization, okay, which you will see in the second course on quantum field theory. So this is certainly not the only way to quantize gauge theory, but this is one way, right? Using this constant Dirac's formalism.
okay. Yeah.
Any other question? Okay, so I think I'll then stop and then tomorrow we'll continue with this lecture.